And I'm going to start again here for the body of the lecture. So during our last session together, Shayan had introduced a very important topic. Very important, again, for these two sides of the types of issues alluded to in this course, namely dynamic modeling on the one hand and data science support on the other. And specifically, she had spoken about data migration and data migration functors. So if we have a functor from C to D, she had noted category C to category D. She had noted you get three canonical functors out of it. One of them is contravariant, going from D instances, so D sets to C sets. It's kind of in the opposite direction, right? We have a functor C to D, but we get a ability to map D sets into C sets. And then there's a sigma migration, which goes in that same order, which has this very free character associated with it. Where we add things if needed, but by default, they're different if we need to add them. And a pi migration where we then when we add things, they tend to be to the same thing. Now, one thing that I hadn't fully appreciated until recently, but John Buys had drawn my attention to it, is this basic picture that you see here. It involved what are called adjoint functors. And adjoint functors involve these adjunctions, these situations where the structures over here on the right are in some sense mirrors of the structure on the left. It may not be precisely mirrors, but the Hom sets have this systematic similarity. There's this not just isomorphism, but natural isomorphism between them. Two-way natural isomorphism. And we had a picture on the board up here last time where I drew those adjunctions. What John emphasized to me is that this adjunction, which pops out, which, I was thinking in the part of my brain related to data migration, and if we have an old category, old schema C and a new schema D, or excuse me, a new schema D and an new schema C and an old schema D, and a map between them, we can update our data to this new situation. Well, it turns out that these functors play the normal role in structured cospans. So I don't know if you remember, but we saw adjoint functors for structured cospans. Do you vaguely remember this? Yeah, there was a category A for the feet. Do you remember that? And a category X for this apex. So this might be a stock flow diagram, and this down here, the category A might consist of like stocks, because you can identify stocks when composing causal loop, stock flow diagrams. You could say this stock in stock flow diagram A is the same as that stock in stock flow diagram B. Do you remember that? But we might also identify some dynamic variables between them. So this would be A was kind of a simpler category. X is like a richer category involving the whole stock flow diagram. And there was an adjunction between them. It was the way to kind of go up from this to this, kind of promote it, right? From a foot category to a apex category, or promote it back. Do you remember that? And we argued that, like, because of that, you could either view it this way or view it that way. The two, because of the properties of adjunction, the two are, mutatis mutandis. The same basic thing, just, with the systematic mapping between them. You could view it either way. You may remember that. And there was also an argument about one preserves co-limits, one preserves limits. It turns out these adjoints, John pointed out, are normally these adjoints here. It's normally delta and sigma. That's what plays the role. So delta plays this role of mapping down from the complicated category to the simpler category, if memory serves me. And the left adjoint, this kind of free one, serves to go from the smaller to the smaller category, sort of interface category, as it were, the foot category, up to the richer category. Okay, so I had a different part of my brain dealing with this adjunction, and it never crossed my mind that it's the same as this adjunction. And his point is, it's the same adjunction. This is normally what we use in structured Cospans. It's just here we think of it as migrating data, but there we're thinking of it as like this, an adjunction having to do with these two, linking up the feet with the whole category, but the apex, the richer one. But it turns out it's the same functors normally. This is delta, this is sigma, which is kind of cool, that it ends up popping up in this other place. Adjunctions, as I think Levere observed, or no, maybe it was MacLean. In any case, adjunctions are everywhere. Okay, so that was a bit of an aside. I did, though, on the face of Jayan's excellent introduction of these functors, I wanted to point out something that I remarked from the seat last time. Namely, these functors, these canonical functors, these completely well-defined functors, if I give you a mapping from C to D, I get these three possibilities automatically. They follow logically from it. That's not the only way to go from a C instance to a D instance. Or D instance to a C instance. There's other ways too. These are just the canonical ways. So sort of always there, completely well-defined, and result automatically if you define a mapping of the schemas. Okay? They're automatically there. If you define a mapping of the schemas, you get these kind of, it's implied. You have these right away. This ability to migrate data. It turns out that that's not the only way to go between like a D set and a C set. Okay? Go this contravariant way. So in CATLAB and in algebraic Julia, that's based around CATLAB, there's really two mechanisms for data migration. The one we saw here are kind of the simplest, they're like the ones that just fall out of mapping the schemas. But there's others that are much more sophisticated that we could define. And for those interested more in the data science side of this, I'll say that there's this support. Well, I should note that queries, when you query a database, you may not have thought of it, but it's kind of like a data migration. You're saying like, select, employee and department from this database, right? And you get back traditionally like a table that shows, employee and department, right? That's like, what I'm going to say is, you can squint your eyes and think of it as like a data migration from a really rich schema to a simple schema involving only employee and department, right? So you can think of like a query as a data migration to what's commonly a simpler schema than is in the database as a whole. You may not have thought about it that way, but it's like that. And what I want to highlight is this recurrent theme in category theory, which is it's not about the pieces, it's about the connections. And while we might think of that as giving us a table, a single table, a set, as it were, employee, department, etc. Actually, the more interesting thing is when we get our whole database, okay, out of it. That has a very data migration feel, right? So it turns out CATLAB supports both of these. Okay, that was very true. conjunctive queries, you can perform querying against a CSET. In fact, you can perform querying against a relational database, but there are these key macros called @query and @relation that allow you to sort of extract information. And we actually use undirected wiring diagrams to express querying. Do you remember where we had undirected wiring diagrams before? We encountered them in this very room. Actually, in I think the last take-home exercise, we encountered them. Do you remember what it was for? We were actually using structured Cospans to put together, in that case, causal loop diagrams. These undirected wiring diagrams. So we said, like, make this stick together with that around this point, and that one around that. Remember that? Like we did it around like smoking. Several of them were linked around smoking. Another was linked around, I don't know, something about social, yeah. Exactly. We use this undirected wire diagram to say like where they come together. It turns out undirected wire diagrams can be used to express queries visually, graphically, and that's supported. In fact, this @relation is for undirected wiring diagrams. I'm giving a kind of little example here where we have two vertices and we want to link up edges. Okay, so we have 3 vertices and you want to find edges where the source of the first edge is V1. Target of that first edge is V2. And then another edge, which goes from V2 to V3. And here we're kind of looking for end-to-end arrows. Can you see it? One from V1 to V2, another from V2 to V3. We're looking for 2 edges. That's kind of how to read that. So these are supported, and you can go read about them in the CSET conjunctive queries, okay? But the one that we've used actually the most is much more flexible than that, okay? It does support this automatically. It kind of can handle that. It can handle these sort of things automatically, detect, oh, you just need one of these. I'll give it to you. But in general, it handles something much richer. It provides you a database back, which again has a kind of data migration feel. You draw from a database and it gives you a database with a somewhat different schema back. And the key thing here is @migration. It's always in a contravariant direction. It's always like this. Remember we had a schema, we have a new schema C and an old schema D, and we want to bring things, a database encoded in the old schema into the new schema. Remember that? It was contravariant. We could do it simply by pre-composing. If we have something that goes a D set, we can, and we know how to map C to D, then we know how to map C into a set, right? That was the idea. This also is contravariant, but here's the deal. Normally, for a functor, this is a functor. This is a functor. It's an adjoint functor, but it's a functor. Functors map what into what? What do they map? Objects to what? What does a functor do? Where does it map an object? Maps it to a what? It's not a trick question. Maps objects to, what does a functor map objects to? You tell me. Objects to objects. Thank you. And morphism to morphism, which is often the more interesting thing. Well, here, we're going to be mapping, for in this more general case, we're going to be mapping objects of our, say, new schema into a query, okay? Excuse me, into a query. So each object here is going to turn into a whole query that tells how to collect the information needed for that object, how to get the goodies for that object, how to gather them from this other data set. It's like how to gather things needed here from this. Okay. And so often we think of like C prime as like an extended schema. We want to populate with this newer extended schema, and we want to populate it from a C set, an older C set. And this gives us a really flexible way to do it. So even if it's not one of these queries, not one of these data migration functors, we can have a more sophisticated one that gathers the goodies here to deduce them here. Are we okay with that? Okay. So it turns out DataMigrations.jl has a great use for this. Okay. Now it's still kind of bleeding edge. The goal for it is, and I don't know quite where it is, but the goal is to real soon now, and maybe it's already in place. It's functorial. And when we say functorial for something, it means it not only maps objects to objects, but what to what? Morphisms to morphisms. It can lift morphisms automatically. And that's going to be pretty valuable for us. Okay. So it turns out that data migration supports sort of a hierarchy of queries. This is a disjoint union of conjunctive queries. Possibly Larissa will remember this. A duck query, disjoint union of conjunctive queries. And it turns out this one down here is one of these. And you can have conjunctive queries or disjunctive, or. And this allows to have more sophisticated form. And basically data migration figures out what type you need based on your query, and it does the right thing. So I want to give you a flavor of data migration because we're going to be using it for our rewrite rules. Again, this is one of these things where these concepts touch a lot of things, just like adjunctions earlier touched a lot of things. They were about data migration, but they're also about this structured Cospans. Now, these migrations not only come in with migrating data, not only come in with structured Cospans, they come in also with migrating our rewrite rules to broader content. So we're going to see why that's so important. So we can have a rewrite rule formulated without reference to networks, and it can automatically now operate in the presence of networks. Okay, so let's take a look at the syntax for this rewrite rule before I show you a bit of syntax that Shaoyan wrote, okay? So this is syntax for this data migrations use, where the use at migration. And if you squint your eyes, you can kind of understand it. It says, okay, look, if I want to go from this to this, if I want to go from one of these to one of these, or this instance, which is graph, to this instance, which is a port graph, I want to map V to box. I want to map E to wire. And I want to map source to, down here, source, and then box out. And actually, I think it's contravariant, so I think it's in, no, I think that's right. And then target, this one, target to box in. And basically, this provides something that's very consistent. E went to wire. And so source maps to the thing V has to go to. V went to box. So we go over from sort of where E went, or E came to where V came to. And same thing here. So this is a little simple example, but they can get much more rich. I mean, consider this. Okay, we have a schema graph. So these run on any C set. We have a schema graph. And we want to find, so we have something encoded with this. We want to find all edges, all pairs of edges, end to end, all paths of length too. So we want to map V to V, the same set of vertices. We want to map E to two edges where the source or the target here of E1 is the same as the source of E2. So they're end-to-end. And then we have to say what the source is for that end-to-end path. Well, the source of the path length 2, the source for that is the source of E1. And the target of that pair is the target of E2. So here we have formulated a little data migration functor that essentially can extract from a graph all pairs of length 2. There's another one in this presentation which extracts all paths less than or equal to length 2, which you can see. Now, you may be excused for wondering, well, what of it? I mean, like, what does this have to do with algebraic ABMs? Well, it turns out it has a lot to do with algebraic ABMs. And one of the big needs there, and we'll be commenting on this in a broader context in another few minutes, is that we may have a rule formulated, again, without reference to a network. So someone's either S, susceptible, infected, or recovered. And now suddenly we want to bring that into a broader context, like a schema where you have edges and people are the vertices. And there's some extra rules here where, like, a person is connected to themselves or what have you. And every edge has a source and target person. So here, in order to do this, what we're going to be doing is we're going to be taking a rule here and bringing it into this one. Do you see that? So that's the idea. And this is really important because rules involve morphisms, okay? Morphisms with respect to this. And we're lifting the morphism, or like translating the rule, including the arrows in it, right? Not just the objects, but the arrows, into this broader context. And it turns out you can do this by this here. If we call this C and we call this D, the richer schema. D, person maps to person. E maps to the product of P and P. Source maps to P1 target. And so I'm not going to explain all this, but suffice it to say that this language of migration here is much more general. What's going on, again, is objects are not mapped to objects. Objects are mapped to queries. Here, or you could think of them as being queries, okay? And morphisms yield map between queries, which is kind of interesting. So data migrations end up playing a big role in practice for us. We use them to kind of translate things between areas. And to that end, I'm just going to show you a bit of code that Xiaoyan would have presented had she been able to be here today. This is VS Code. How can I, like, what can I do? Can I, like, zoom in on this? Oh, here we go. Control plot. Control equals. Here we go. All right. Okay. So this is an SIR model, and I'm not going to go through this in all its detail. But what I will say is, here's a migration where she is updating migrate metrics and AC sets from a pure state chart schema to a composed model. So here she's translating data, rules, for example, translate from a smaller context into a larger context. And I'm not going to go through the details, but basically you can do this to allow, for example, if maybe without reference to networks, if two people, A and B, A can infect B, okay? A can infect B. You know, an infective, in other words, together with susceptible, yields 2 infectives. You can imagine, right? It's a simple rule, right? You have a susceptible and infective. The infective can turn the susceptible infective. Can you imagine that as a rule? Well, what this can allow is you to say, well, okay, we have this rule. We're going to translate it to a network. And what in a network context it's going to mean is that if A and B, the susceptible and the infective, are in neighboring vertices, if they're one edge apart, then the infective can infect the susceptible, but only under those conditions. Or you might say if they're moving around in space, right? Hopping between locations, they have to be at the same location for one to infect the other. Same rule can be translated in different ways depending on your needs for the broader model. So you can define the rule of infection kind of without having to hard code what your assumption about context is. And then you can like lift it to the appropriate context. That's the idea, okay? That's the idea. And this shows it being lifted to a context where like they're one edge apart. So this issue of data migration, it's not just something which comes in for migrating between databases, as important as it is for that. It's certainly not just about these wonderful canonical functors, as wonderful as they are, automatic and sort of wholesome as they are, and how frequently they are useful. It's not just even about structured Cospans. It's about being able to lift morphism, being able to lift rules for rewriting from an error context to a bigger context, eh? And this migration syntax provides this very powerful way of basically defining queries that gather the information from here needed to populate the broader schema in a rule-based context, okay? So that's the idea. We don't have time to go into it in detail, but if you understand it from that perspective and you consult some of the documentation and review a video or two, you can understand how to put together these little rules that say, hey, this is how I want to generalize that rule to this context. And you can generalize it in this way, lift it up to this other context. And you could lift it up to different contexts. Are we okay with this idea?
I have a question for the code.
Question.
What's like if you go to the code?
This one?
When the Xiaoyan
Yeah.
for the migration,
Yeah.
I saw the ID.
Yeah.
Why?
Yeah, that's a good question. So at first we didn't have ID.
Yeah.
And so there was a textured discussion of this. So I'm not saying this is the only need, but I'll give you an example of where it came up. We were visualizing the network structure. You can do these, have a network structure post, and you can watch infection spread across this network. The problem is that when we were running it, over time, the network structure might look different. And we couldn't tell who was who, right? Like in relational data, remember this idea with that with combinatorial data, with the relational data, what you don't care about who's person one, who's person two, who's person three. That's more like what you deal with attributes if you want to keep track of the values. Rather, you care about the relationships. But if you're visualizing a graph, you actually care like the person shown here is the same person every time. So I could see them get infected or see them recover. And without that ID, we couldn't say, oh, that's this person here got infected in the next time step. They were susceptible, now they're infected, because it can shuffle their numbers in the C set and in the set for person. Do you see what I mean?
Yes.
It's like maybe before they happen to be person 1 in the C set and in the set of the arbitrary ordering of the set of persons, and now they're person 23, and we can't reason about like who's who. Is this the same? So we wanted to trace that in fact the infection was spreading in a sensible way, and we couldn't do it without IDs. And so this was one way Chris Brown had suggested, okay, look, you could give everyone an ID, then you can track this is the same person as before. It's not, probably the mathematician in you is not,
And also ID
uplifted.
VID to VID, so same idea, right? The ID for the vertex.
Yeah, I'm a little bit like, I don't remember VID compared to ID, but I think it's probably, yes, you want the vertices to be shown visually. It'd be clear, like this is this vertex, this is, you don't want to like,
Oh yeah.
you don't want to like shuffle. No, what's preserved, of course, automatically without these is the relationship between people and vertices, but sometimes you really care like about tracking. Okay, this vertex had nobody in it, now someone's moved there, someone got infected there, like you care about those things. And adding IDs let us do this. Okay, it may not be the only way, but it was the easiest way recommended. Does that make sense? Yeah. It's a pragmatic matter. What it lacks in beauty, it makes up for in utility.